Okay, you're welcome again. We are still proceeding with our question, and we had so far obtained the empirical formula. We now wish to advance and look at how to get the molecular formula. Now, but like we said, when we are discussing this molecular formula, we said it's about total number, or expressing the actual number of atoms present in 1 mole of a compound. Just that. This is the ratio. 3 carbons to 8 atoms. 3 carbons to 8 atoms. But exactly how many carbons are there? So this doesn't mean that the number of carbon atoms are 3, but simply shows the ratio of carbon to hydrogen. However, you could go ahead to obtain a molecular which is the same like the empirical. That is acceptable. But the empirical expresses the actual number of carbon atoms in a given molecule. So let us advance. Okay, now molecular formula. That is part B of the question. Now, to obtain molecular formula, we definitely need molecular mass. But unfortunately, the question doesn't give us molecular mass. But luckily enough, it gave us the vapor density. We are given vapor density. To have molecular formula, you must have molecular mass. But molecular mass is not given, only that we are given vapor density. But we have a relationship between vapor density and molecular mass. And I want to say that molecular mass is equal to 2 times vapor density. It's supposed to be 2 times vapor density. So the 2 is a constant, but the vapor density is 22. So when we work out, we still get 44. So that means, therefore, the molecular mass of compound Q, which is hydrocarbon, is definitely 44 is the molecular mass. So then we write a relationship between the empirical and the molecular mass. And the relationship is that the empirical formula multiplied by a factor n which we don't know should equal to the molecular mass, which is 44. So we're going to work out the empirical formula, find the value of n, multiply the value of n by the empirical formula, so that we shall be able to obtain the molecular mass. The molecular formula. This is 44 equal to, carbon has atomic number 12, atomic mass, but there are 3 atoms. And I want to encourage you that it's supposed to be atomic mass first times the number of those atoms. Not number of atoms times. It's supposed to be atomic mass times the number of atoms. So this is hydrogen has atomic number 3, mass 3, 1, but there are 8. But all of these ones have been multiplied by factor n. So when we work out, this is 36n plus 8n equaling to 44. 36 plus 8 get 44. So we are going to have 44n, 44 equaling to 44n. Divided through by the constant. This is 44 out of 44n equaling to 44 divided by 44. So therefore we shall have 1 equaling to n, and therefore n equals to 1. So therefore it means that if we're looking at molecular formula, we should have the empirical multiplied by n, and this time we know our n, which is 1, and therefore we get C3 H8. So this is our molecular formula, and that is how we can work it out. That makes part B of our sample. Okay. Now from there we want to advance finally and look at the structure formula. Remember, we are looking at empirical, molecular, and structural formula. Now, finally part C, structural formula. Structure, I say the structure simply shows the bonding. We have obtained our molecular formula, but how do those atoms bond to one another is what is important. First of all, knowing how they bond also means that we should know the homologous series to which this molecule belongs. Yeah, right now we have not yet studied so much about homologous series, but we can beep there because we have to look at it ahead. Homologous series, and look at this compound with the CH3H8 corresponds to a general formula which is CnH2n plus 2. That's what it corresponds. And this is a general formula for all alkanes. Of course, we are yet to look at this, but I'm simply bringing it in to look at the homologous series to which our hydrocarbon Q belongs. And once we can realize that it conforms to this general formula, then we shall know it is an alkane. And after knowing that it's an alkane, then we shall know it is composed of carbon-carbon single bonds, which are sigma. So this is a carbon. We can express it to another carbon. We express it to another carbon. Only that we make sure that bonds reach where they are going. We should avoid hanging bonds. Those are 3 hydrogens, carbons. They are able to connect with one another because these are carbons. And carbons, we say, they undergo catenation. Catenation is the ability of carbon atoms to form long rings and chains. Now, each carbon atom should take a maximum number of 4 bonds. Every carbon should take a maximum number of 4 bonds. Now, that one means we should try to allocate where do the hydrogens go. That's what we're doing now. So this is hydrogen. That is now the structure of our compound. I don't want to go into nomenclature because that's the next agenda here. But now we can rearrange it in a more simpler form. Instead of writing it, because it is occupying a lot of space, even writing it takes a lot of time, we can say that one does not differ from somebody who writes it in this format. These are 3 hydrogens on that first carbon. Then this carbon is having 2 hydrogens. So we can also go ahead and present it that way. Then finally this carbon is also having 3 hydrogens. So that is how we can represent it.